Okay, let's hope for good. And we are putting quad 3 for the time being behind us and moving to a different data structure called R trees. And R trees are very, very general, can contain a lot of type of geometric, geographic, multidimensional data. Triangles, segments in my slides, non-intersecting segments in my slide, the R tree doesn't care about. What you're doing with your data, it can be moving points, single points. And it's good to answer all the type of queries that we discussed earlier. And it has several other properties that we'll mention very soon. So here is the general description of the R trees. So first, note that if I give you an object, any geometric object, and I ask you to find a bounding box of f, the name of this guy is f, and the bounding box of f. When I'm saying bounding box, I always mean the axis parallel bounding box. That is, the edges needs to be parallel to the boundary. So I'm looking for an edge that will be parallel and will bound my shape f from the left, which is just a very complicated way to say find the minimum, the point with the minimum x in this whole curve, the point with the minimum x, the point with the minimum y, the point with the maximum x, maximum y, and this will be the bounding box of f. Just find max mean of x and y, and if there are more dimensions, then do it in more dimensions. Now, while my input here is a set of segments, triangles, anything you want, and for each one of them, I'll find its bounding box. And I'm going to describe the tree in a bottom-up, except that my tree has a root down, so it will be from the, but I'm going to build it from the leaves toward the root. I don't know if it's bottom-up or if I draw the tree in this way, but it's from the leaves toward the root. So to start with, I put every segment is, I pick its bounding box, and with the leaf, I keep the bounding box of the leaf. Now, there is tons of questions about it. How should I order these segments? Essentially, I want to say two segments that are close to each other should be close to each other in the tree. But there are lots and lots of PhDs and papers and publications about how to build R trees with various heuristics or various strategies about how do I arrange the order among the trees. But the basic description of the R tree stays the same. Leaves corresponds to the bounding box of the nodes. This will be level 1. And now I'm going to pick two segments, hopefully that are close to each other, and I'm going to merge them. Merge them means what? Pick two of them, say these two, compute their bounding box. But here's the fun thing about the bounding box. If I have two bounding boxes, and I want to compute a new bounding box, of all the objects, a new bounding box that encapsulates these two bounding boxes. I don't care one bit what are the segments are. I just care about what is the max and the min of the bounding box themselves. Okay, so I just look at the x and y coordinates of the two bounding boxes, and what I stored in the common parent of 7 and 8, what I stored is a bounding box of a new bounding box of 7 and 8. So a new bounding box of the bounding boxes of 7 and 8, to be precise. So that would be what I denote as a bounding box of 7 and 8. And that's what this node corresponds to. Now, it's not a hierarchical data structure. It's not a hierarchical data structure. It's going not to be there. Take 5 and 6. 5 and 6, the bounding boxes, merge them and compute the bounding box of 5 and 6. Similarly, take 3 and 4, compute their bounding boxes, bounding box of 3 and 4, and compute the leftover 1 and 2, their bounding box is stored over here, and that's what I stored in this node. So now I concluded level 2, and I'm moving to level 3, which would be just the same policy. Pick 2 of the bounding boxes. The order, again, of course, influences the efficiency, and there is a lot to say, but essentially I want to merge bounding boxes once again that are close to each other or overlap. I might be lying about the hierarchical. It is hierarchical. So this will take bounding boxes 5 and 6, 7 and 8. Here is a purple bounding box that encapsulates inside it the segment 7, 5, 6, 7, and 8. But remember, the node doesn't care about the segments, just cares about its bounding boxes. And to compute this bounding box, I just need to look at the immediate children. So that would be this bounding box of 1, 2, 3, 4, and at the root will be one big bounding box of everything underneath. Okay, so I was lying. It is a hierarchical in the sense that the two children, their region is inside the children of the parent. The bounding box of the parent encapsulates every other bounding box. What is not true, as opposed to quad trees and as opposed to other trees that we are going to see, is that the two children divides the plane between them. They do divide the data, but their bounding boxes can happily, the bounding boxes of 7 and 8 can happily overlap. It's fine. The root of 7 and 8 is still happy with its children overlap its region. We hope that this overlapping region is not large. The height of this creature doesn't require too much negotiation. If I start with n segments, I'll end with a tree whose height is log n. Not much to say about it. Some animations that I forgot, of course. If I have a reporting, I'm given one of our standard types of reporting. You're given a query region. As usual, the query region is usually a square or a rectangle itself, but easier in the slide to think about a disk. And I want to find all the segments that intersect the query disk. Or I want to find all the segments that are contained inside the query disk. Or I want to find their numbers. Or I want to find either emptiness queries, either any segment inside the query disk or not. And the report procedure is very standard for us, the same that we're using all the time. Given the query region and giving the root of the tree, I'm caring about the three general cases. Either the region of the bounding box at the root and Q, they might be disjoint to each other, far away from each other, just like in the quad tree, or it might be that the bounding box of the root is fully contained inside the query region. It's huge, it contains all the segments, or it might be that they partially overlap. So I check all these conditions, again, between bounding boxes, not between two disks, but between bounding boxes to check if one is inside the other. It's really easy, right? It's just comparing x and the y's. So if Q does not intersect the bounding box of the root, then we are done and return. If the bounding box of the root is fully inside Q, then all the segments in the tree are inside Q. In the tree, what? In the tree that is rooted at the root, it's going to be recursive. I'll ask you something about the tree rooted at this purple node, and you're doing just the same. It's just, you're talking about the trees, about the segment that corresponds to the subtree rooted at this purple guy. Okay? If the root is a leaf, could be either because of the recursive or because our segment width is so tiny. If the root is a leaf, then depending on the query, there is some segment inside the leaf. Is this intersecting the disk? Does it not intersect the disk? We need to check it personally about this segment directly. Then we cannot use bounding box anymore. And going back one step that I did not mention, if the bounding box of the root is full inside the query region, then if I want to report the segments inside the query region, then I need to go to each one individually. If I just want to count them, and if I'll store for each node how many segments it corresponds to, then I can just add this counter to my overall counting. Right? And finally, if none of these cases happens, that is, the bounding box of the root intersect with the query, but the query doesn't cover the whole bounding box of the root, then I'll send the problem recursively to the two children of the root, and they just do the very same thing. And of course, what you hope is that this matching algorithm was kind of smart about how did you build who the clustering part will be smart so that you will not be in a position that the query intersect many bounding boxes, yet the query doesn't intersect any disk, any segment. It definitely could be, but you hope that it doesn't happen too often. But if I would decide that 1 and 8 are matched together, then almost every query will have to visit this node just to realize that, to visit this guy, just to realize that the query problem doesn't intersect the individual bounding boxes. Yes, sir?
You're seeing something, is the ranking log in time?
Query? Absolutely not. I mean, you don't know, but definitely not log n bound.
But you're seeing something is in log.
The height is log n, but because of the recursion, possibly I'm visiting the whole tree. Nevertheless, R trees are extremely useful, both to finding nearest neighbor, to finding who is around me, to finding geometrical data that is more complicated than just points, or objects, robot parts. Yes, sir?
Do the line segments have to be ordered left to right?
No, I just highlighted it so I'll know how to merge. But essentially, I can create the order from seeing who is merged with whom. But what is the left and what is the right is completely arbitrary. Right. No meaning here. You have, as the next slide shows, you find many papers that discuss good heuristics. When you want heuristics that will be nice when you're inserting and deleting segments, when segments are moving, when players are moving, and so on. Okay. Let's talk about R trees in the real world. So what happened in the real world? Assume that a model of your memory where you have expensive, very fast, but limited in size, high-level memory. Let's call it the main memory. Generally, we are talking about the whole hierarchy, but let's just divide this hierarchy into two. So there will be a fast, we will have a main memory that is fast, very fast, but has more limited memory, and some secondary memory device that can store much more data, but is much slower. And what I'm telling, and if you're saying, I don't have a hard drive, I have an SSD, it's still correct about it. Your SSD is still much slower than your main memory, higher level on the cache. Okay, so how do, what does it takes time when we are talking about hard drive? We are saying, why do I need the hard drive at all? Why do I bring it up? Well, what happens when your file is too large for your main memory? Or too large for the level of the memory that you want to store it in? Then you need to use then pieces of your tree, maybe not all the tree, but most of the tree is on the slow memory, on the hardware. And there is part that is very relevant for disks and also relevant for SSD that says there is a seek time. It takes some time for the head of the hard drive to get to the right place and for the hard drive to rotate until it gets to the right track that you are looking for. And once it does, then you usually don't read only 1 byte, but you'll read the whole bucket, a few kilobytes of data in general. Okay, that's a minimum unit of memory that you're doing I/O with, either write or read. And by the way, SSD has a bit more interesting issues that write is much slower than read. So in a sense, it suggests slightly different problems. And these two facts make it really interesting to arrange the tree inside the hard drive. Or how do I store our tree in the hard drive? So what I will do is saying I will think about an R tree, but now a node, an internal node is not corresponding only to 2 segments, but maybe to 3 or 4 or 100. 100 sounds like a good number. A leaf will store 100 segments. Its parent will store 100 bounding boxes. Its parent will store 100 children, and so on. I'll go for a degree that is larger than 2. Here in this example, the degree will be 3. Every node has 3, and this is actually an example of B tree that also shows how I can insert and delete nodes, and it goes very dynamically and nice. But the common theme about both an R tree and B tree, when you're using it in practice, is that you'll go for much larger degree. Every node will have a lot of data. Why? Because what I actually count for in running time is, think about point location. Point location in the R tree will start from the root. Say, hey, point, is the root cover you? And if yes, in which of the children do I need to visit? Maybe more than 1 because the boxes are not disjoint. Where do I branch into? Correct? So but that means that I need to go and fetch a few of the children, and what I count for is how many fetch operation do I do? How many IOs operation do I do from the tree? When I'm going and moving the head of the disk to the right place, then I can read a big chunk of information. So a node might be large. In terms of CPU time, I'm making life slower. This is slower than R tree with degree 2. But in terms of I/O, which is usually the bottleneck, it will make life much, much, much faster. Let's see why. What I really account for is what's the length of the path when I'm visiting a leaf. Let's say that I'm only visiting 1 child of a node. I'm looking for what is the length of this path, because that's a number of times that I need to move the head of the disk from one place to another. That's the real bottleneck. And I want to tell you that it's much better to store a tree which is much higher degree. Let's say degree is 100. A node stores 100 segments or 100 bounding boxes. It has 100 children at this time. The CPU needs to work harder. That's fine. CPU is fast. Let's think about a mid-size quad tree. The size I'm storing a billion, 10 to the 9, many segments. If my quad tree has degree 2, every node has only 2 children, then the height of the quad tree is log to the base 2 of billion. How do I compute it? You know, log to the base 2 of 1,000 is 10. Log to the base 2 of 10 to the 9 will be 30, meaning that I need 30 IOs to access one of the leaves, if the degree is 2. But an IO brings a lot of data, so a node can be large, can contain more than just two children, can contain the addresses of many children. So if instead I will store 100 or 1,000 segments per each one, then what is log to the base 1,000 of, where did it go? Log to the base 1,000, which is completely realistic. If I have a few kilobytes per node, I have enough room to store a few hundred or a few thousand children. Log to the base 1,000 of 10 to the 9 is only 3. Meaning that the height of the tree decreased to 3, meaning that the search will take only 3 IOs. And actually, the good policy would be keep the root plus the first level in the main memory. So you don't need to access the disk or the secondary memory for the root and the first level, and only the leaves are stored in the secondary level. So it's only one IO to visit a leaf. So that's where how outreach are used in practice, and what brings them their popularity. And by the way, if your data is one-dimensional instead of multi-dimensional, that is, you just have keys, IDs of students, something that you can compare to what is to the left of what, then these R trees has a slightly different name. They are called B trees. And they are really cool. And they can even handle insertion and deletion very smoothly with log n time per insertion and deletion. You can do it also with R trees, but it's not as smooth. Everybody understands what's going on here? People, are you good? We are slowly accumulating enough material for homework 4, so that we're getting there. Okay, we're done with this type of trees, and let's move to more trees. Okay, by the way, the material that I'm discussing today is really, really practical, really influential, much beyond the theoretical world. Okay, back to input, which is a set of points. Everything is in main memory right now, and I want to tell you about KD trees. KD trees in general dimension, and in two-dimensional world, they would be named, and it's a terrible name, they will be called 2D trees, which is as meaningless as it can be. And they are separated from range trees, even though there are ranges in all our trees. So plenty of room to be confused. And I'll ask you a few questions that ask what is good and what is bad in each type of tree. Okay, so I have a set of points. Yes, they are used also for other type of data, but let's describe them for points only. And I don't want to use quad trees. I want something with a bit more theoretical bounds, and it's not practically bad. So what do? I take all my points, the same type of queries as usual. You have a query region, how many points are there, what are the points that are around you in certain distance, who are the other players, and so on. All the standard, the same type of queries. In 2 dimensions, I'm going to build a tree by taking all the data points, call them the root, and now I find the median in the x dimension. Find the median in the x dimension. Look at the x value of all the points, find the point in the middle, or 2 points that are between them is the middle, and now you have n half many points to your left and n half many points to your right. Okay, that was a split by the x. As a pole, now in the quad tree, we may choose that the vertical split will divide the area in every side to exactly the same area. The sizes were the same. In KD3, I cared about the data. I cared how many data points. If this line that I split is more to the left or more to the right, I don't care. Okay, that was my first split. Now I'm moving to the y direction, and I take all the points on my left side, and I split them. Take all the points on your left side and find their median, but now their median on the y value. So I started with n many points, n half to the left, n half to the right, n quarter in each one of these quadrants. And again, no commitments to the geometric equality between them. They should contain, however, the same number of points, plus minus 1. If I have another dimension z, then now I split in a direction that is orthogonal to the z-axis. That's the z-axis, so now I split by a direction that is orthogonal to the z, and back, and my next split will be again back to the x. So x, y, z, x, y, z, x, y, z, etc. Two dimension, it would be first by x, then by y, then by x, then by y, and so on. And that's KD trees. That's the theory, or big chunk of the theory about the KD trees. Okay, so again, split by x, and so on. And now you see what is a quad tree. And what's really confusing when I show the KD tree, what's really confusing is what a node corresponds to, which is as usual some region in the plane, versus what a node stores. So let's see what a node needs to store. So every node in my KD tree is going to store a line. And this line is going to be horizontal or vertical. So actually what the node needs to store is just a number. And I'll understand if this number corresponds to a vertical line or a horizontal line based on, I know that I first split by x, then I'll split by y, then I'll split by x, then I'll split by y, and so on. So I know how to understand this number. So that's what a node needs to store. Now, let's separate it from the region that a node corresponds to. A node corresponds to a region, just like in the quad tree. So the root will correspond to my whole region over here. That would be the, let's move it. The root, then R of V is the whole blue region over here, and I have various data points, and I store the x coordinates of the line in the median. So what I stored here, if this line is x equals 17, then all I stored in the root is the number 17. I mean, it's a bit anachronistic in the way that people really were struggling with bits, minimizing bits. Now, the left subtree, how do I know what is the left subtree? I look at this line, I look at R of V, and I say, here is a region that is R of the root intersected with edge, the half plane 1. What is the half plane 1? Everything to the left of this line. So when I'm visiting this node, I know that the region that it corresponds to was what the parent corresponds to, intersected with one of the half planes. Make sense? So the red node will correspond to this region. And I'm spending much time about it because when I was exposed to it, I found it very confusing. The white subtree will correspond to the root, or the range of the root, intersected with the opposite half plate. Everything over here. And if let's use all the wonderful markers that I bought, and if I go to the right subtree and I'll go to the lower left subtree, then R of Who is it? That would be R of U3. Would be, first I need to store, well, I stored it here, the y coordinate of y equal 19, vertical line, and the region that the root corresponds to is this part, everything below it. Okay. Yeah.
So each node will store whatever region the line is splitting to?
If you want to save memory, since usually you start from the root of the tree when you access nodes, then you don't need to. I mean, it's nice for other purposes to say, for debugging, that every node will know what is its region. But essentially, once you tell me what is the path, then I don't need it. I just intersect it with, if I went to the left and it's an even node, then I'll understand it as split by y, otherwise split by x, and left to the right will be either, left node will either be the left side or the lower side, depending if I'm on the x and y. So from knowing the path, I know what is RV. Okay, and of course the height is log n. There's not much to discuss over here. How much time does it take to build it? Sorry? I mean, it's older to the end in the sense that it's no more than to the end, but no, that's a very pessimistic bound. Correct, but no, it takes less time. You don't need. So to build it, I need to sort the points. If I have to sort them, then it's at least n log n. But if they are sorted, well, if they are sorted based on x, and also sorted based on y, then what do? I looked at them sorted by x, pick the median, you split them into 2 halves. So it takes linear time. Then you look at only the left ones, they are sorted by y, pick the median, split into 2 halves, etc. So you just need to double the data and filter out the other ones. So the overall running time is n log n. You need to be a bit careful that they are sorted and then you're deleting, but at every level you're spending linear time. It's just like merge sort. Okay. Range reporting, repeating our standard tasks, just another slide that I didn't want to dump. You have a query region, query axis parallel region, and you're just asking for every R of V, is this inside or outside, or partially intersect. And if I'll make sure that every node knows how many points it's stored, then every time that I see that R of V is fully inside my query region, just take this counter and add it to the overall summation. We have seen it with all of the other data structures. Okay. A bit more interestingly is, can I finally bound the query time? I couldn't bound the query time for quadries. I just said, yes, in practice it works great. It saves us visiting a lot of nodes that we don't need to. Nor could I set it in R-trees, even worse. Can I finally say something about KD trees? And yes, there are some bounds. They are still quite pessimistic. There are some bounds still quite pessimistic about how many nodes will I visit by a query, just to show you the query. And let's see what is the bound for the query. And you know, let me flash another slide. So here is our structure of the here is a general node. So what you see here in the tree is basically the root. It's two immediate children, and their children that corresponds to these four quadrants, right? U1, U2, U3, and U4. And I perform a query with an axis parallel. Query with axis parallel rectangle. So now my query region stops being a disk, it's going to be an axis parallel rectangle. And I want to ask, what are the nodes that I have to go into them when I perform the query? If my query fully contained is fully outside, if my query region is fully outside, my query region is fully outside RV, I don't need to visit it, obviously. If my query region fully contains RNVs, then I don't need to branch into it. If I just want to count, then I see this node V, and I just need to sum it up. So my real question is, how many nodes V crosses the boundary, or let me call it the query rectangle Q for distancing. It's still rectangle. So how many nodes V crosses the boundary of Q? Well, I'm obsessed with the boundary of Q, because if Q, so if its boundary is disjoint from RV, that RV is fully inside Q, then I visit it, but I don't need to branch into its children. So I'll count it only once. Similarly, if RV is completely outside. It's the cases that RV crosses the boundary of Q, where I need to visit both children of RV. So I want to count the number of such nodes with this property. And to bound it, I'll actually do the following. Pick an edge of Q and extend it into a line L. How many nodes crosses or cross L? So I look at RV, I look at the lower edge, and I say, if there is some node V such that RV intersects the boundary of Q, then it also intersects the line that supports this edge, the line that contains this edge. Maybe it's a vertical lower line, maybe it's a horizontal upper line, maybe it's a right line, maybe it's a left line, but it must, now of course I overcount by this, but I don't overcount by much. I'll replace the edge of Q by the line L that contains this edge, and that's the same question. How many nodes V has the region RV crosses by L? And now I need a simple observation from this slide. Let's take L, you see L. How many nodes can my line cross? Depending where I place L, place it here, it doesn't cross any. Yeah. I'll move it a bit. How many nodes can I cross from this tiny tree that you just showed in this picture? At this moment, my line L crosses 2. shift it a bit upward, it still crosses 2. Shift it a bit upward, still crosses 2. And it will be, as long as my line is either horizontal or vertical, I cross at most 2 regions. Take the vertical line, 2, 2, 0, less than 2, even better. Okay, so at every moment, I'm visiting, if you look at the line L, how many of the grandchildren of the root do you visit? The grandchildren of the root are these 4 quadrants. How many of them do you visit? 2. Which 2? I don't mind. Let's say this and this. But no more than 2. That is, out of all the inputs that consist of n nodes, I visit n half, but that's not really where I want to go with this. Where I want to go with this, and that will be our summarization today, is that formally, if you look at the recursion formula, how many nodes do you visit at level n? You're visiting, each one of the quadrants has n over 4, and you're visiting 2 of them. So it's 2 times the query recursively of n over half, n over 4. Which I hate. Recursion formula, I don't find them very intuitive, so let's play with the numbers. Let's say that n equals 2 to the h, for some integer h. N is a power of 2. So I start at the root, and then I'm going to only 2 of the subtrees. Oh, the font is too small, but how many do I visit at each level as I'm going down the tree? Here I have, if n is 2 to the h, then as I'm going down 2 steps in the recursion, I'm only visiting 2 to the h half. On every 2 steps, you're only doubling the number of nodes that you're visiting by 2. Again, you're splitting by 4, but you're visiting only 2 of them. So how many nodes can you visit? 2 to the height of the tree divided by 2, which is what is n? What is 2 to the h is n? So n half is square root of n. So that would be a bound on the query time, kind of pessimistic bound, but finally we have a bound on the time for a query. So once again, we definitely can, because of the query might spread into a few children, multiple children, it's not only one child of a node, but still the total number of nodes that you'll visit is bounded by 4 times square root of n. And every other node is somehow counted. That you're visiting, you don't need to branch into it. You see this node, and you reject it immediately. It doesn't cross the boundary of the query region, so you just visit the node. And either report all of it, or just add it to the general count. That's it. So yeah, it's about KD trees, and then range trees that are mostly theoretical will come up next. Thank you, and you'll have homework for coming up.